Hey everyone, welcome back to Everything is Relative. I'm Mr. K, and today we'll be doing a crash course on the topic of ideal gases for Cambridge A-Level Physics. So, the topic of ideal gases is sort of the introduction to thermodynamics, or leads us into thermodynamics. And the topic of ideal gases is hugely important because although we'll do this crash course covering only the concepts required, the basics of the concepts required for the exams, the study itself took hundreds of years, and it allowed us to link macroscopic quantities to microscopic ones, as we're going to see in this crash course and in the next one on thermodynamics. But where it all starts, as you should know, is the mole. And we first have to define what a mole is. So if you aren't doing chemistry, a mole is simply an amount of something. So if I were to say, provide me with a mole of cats, well, you probably wouldn't find this many cats anywhere on Earth or all over the Earth, but maybe in the universe. 6.02 times 10 to the power 23. So 1 mole of cats is 6.02 times 10 to the power 23 cats. That's a huge number. This number is what we call Avogadro's constant. It's basically the number of carbon-12 atoms in 12 grams of carbon-12. So it is not completely abstract or arbitrary. And I have to make sure I spell this correctly. AVO, Avogadro's constant. And so this is the number of, well, whatever you're counting. So we call it NA, uppercase N with the subscript A. And so if I wanted to know the amount of oxygen atoms in the sample of gas, I would say 1 mole of O2 atoms, in this case the diatomic atoms, it would be 6.02 times 10 to the power 23 of that thing that I'm counting, O2 atoms in this case. So it is just another way of counting. If I ask for a dozen eggs from the grocers, then that means I want 12. And so instead of saying 12 eggs, I would say a dozen. So a mole is a method of counting because in a standard sample of gas, or for gas in a room, even in a small cylinder, for example, we aren't going to have a small number of molecules. We're going to have on the order of 10 to the power 23, 24, 25 molecules or atoms. So a mole is a more convenient way of counting the amount of gas when we work with gaseous samples. And so the equation to relate the number of moles to the number of molecules is little n equal to big N over Na, where little n is the number of moles of whatever gas you're dealing with, and big N is the number of molecules, 10 to the power 23, 24, etc. So that's number of molecules divided by Avogadro's number, or Avogadro's constant. And so this gives us the number of moles of substance. So if I know the number of molecules, I can quickly go and get the number of moles, which should be a number that's on the order of magnitude of 1 or 10 or something like that, generally, for our purposes at least. I can also write the number of moles as the mass, the total mass of that substance, the mass of 6.02 times 10 to the 23 O2 atoms, divided by the molar mass of that substance, which again you can get from your periodic table. So the mass over the molar mass is simply the mass per mole, which kind of makes sense. The mass divided by the mass per mole tells you how many moles of that substance you have. So this is helpful when we build up to the equation of state, or also known as the ideal gas equation. Again, if you do chemistry, this is more familiar to you. But the equation of state, before we get to the equation of state, we have to sort of, well, derive our way there, in a sense. So, firstly, I'm going to look at a containing vessel, whatever this cylinder may be. It's closed, it doesn't allow any matter to enter or leave. And I have the particles of a gas. So some gas could be any gas, it could be air, it could be nitrogen, oxygen, doesn't really matter. Has a temperature T, it has a pressure P, P1 rather, and volume V1. At some later time, something happens to this gas. Actually, since my artistic skills are terrible, I can just cheat and copy this diagram, and it magically appears over there. So at some later time, I have the same gas. I haven't changed its temperature. Something happens to this gas, but its temperature is still T. It has a new pressure, P2, and a new volume, V2. Again, this is something I would suggest you take the time to read and understand. I'm just moving through it fast since this is just a crash course. But the volume is now changed, and so too has the pressure. It's the same number of moles of gas, basically the same mass of gas. Boyle's law. So Boyle found the relationship that said the initial pressure multiplied by the initial volume is a constant, meaning P1 V1 is constant, and it is the same constant if I multiply the pressure and volume together at any other time when the state of the system has changed, but the temperature and obviously the number of moles remains constant. That means that the pressure is inversely proportional to the volume. So P2 V2 divided by V1 means that P1 is a constant over V1. P is inversely proportional to the volume. Increase the pressure, decrease the volume. Or in this case, we've decreased the volume. We've allowed the gas molecules to occupy a smaller volume, and so they will be at a greater pressure. They will be exerting on average a greater force with the containing vessel, and in that scenario, the pressure on the surface increases as well as there are more collisions with the containing vessel. And in this case, we keep our temperature and number of moles constant. So T and N remain constant. Remember, in this topic, we are considering thermodynamic temperatures, so temperatures measured in Kelvin in general. And then we have our first relation there, Boyle's law, and these are the gas laws. So I'm talking about the equation of state, but I'm starting off with the three gas laws. Some of you may have seen this before, or it may be that in A-level you're seeing it for the first time. Let's take, magically I have my gas appearing. Now let's look at a case where I have a gas with temperature equal T1. The pressure of this gas is P, and the volume V1. Again, now specifically, you can see we're considering ideal gases. So if I take this gas and I change its volume, you can see it now by the means of a piston. Maybe I compress this gas so that it has a lower volume. The new temperature is T2. I somehow managed to keep the pressure constant by adjusting the temperature, and the new volume is V2. Then our second gas law, which is Charles's law, says that the ratio of the volume to the temperature is constant. V1 over T1 is equal to V2 over T2 is equal to V3 over T3, etc. Which means that the volume and temperature are proportional, directly proportional, which kind of makes sense. Increase the temperature and so too will the volume increase. Decrease the temperature and the volume of the gas, you'd expect the gas molecules to come closer together, and at some point they will condense to form a liquid. So the volume and temperature are proportional provided we keep the pressure constant, and the number of moles. So again, there's no gas entering or leaving the system. That's remaining constant. And then for the last of the gas laws, we have, and again, you need to spend time reading this to make sure that you actually do understand. I have a gas, an ideal gas, where the temperature is T1, the pressure is P1, and you can see where this is going. The volume is V. At some later time, the same gas, after some thermodynamic process occurs, has a temperature T2, a pressure P2, so the pressure has changed, and a volume V. Now these experiments you can do in a physics lab, a chemistry lab, or you can watch a YouTube video to see the three of them very easily explained. But this final law is called the Gay-Lussac law, or the pressure law. And in this law we can see that the ratio of pressure to temperature is constant. So P1 over T1 is P2 over T2 is P3 over T3, etc. At any given time, the pressure over the temperature, or consequently conversely rather, the temperature over the pressure is a constant, meaning that the pressure is directly proportional to temperature. Also kind of intuitive, but still very, very important that it was written in this way. I mean, we all have an idea that pressure and temperature are related, but in order to say that they are directly proportional is a big achievement. And so there's at a constant volume and with a constant number of moles, meaning the amount of gas is not changing, the pressure and temperature are constant. Now, if we do a little bit of mathematics and I combine the three proportionalities, I get P is proportional, or rather PV is proportional to T. Write it in this way. PV proportional to T. This proportionality defines an ideal gas. So ideal gases, or when ideal gas will obey this proportionality for all pressures, volumes, and temperatures, provided the number of moles stays constant. And if you look at the definition of an ideal gas, that's what you'll get. PV is proportional to T, which means that PV is equal to nRT. Okay, and this is called the equation of state, or the ideal gas equation. So this is what we are trying to sort of derive. So the constant, going from a proportionality to an equation, required us to add the constant, and that constant is the number of moles. So sometimes called the ideal gas equation. So if any gas obeys this rule, meaning the product of pressure and volume is proportional to temperature, or PV is nRT, then that gas behaves as an ideal gas. Now ideally, poor choice of words probably, but ideally there is no such thing as a perfect ideal gas, but there are many scenarios in which a real gas can behave as an ideal gas. R here, we haven't really mentioned R, not to leave R out, but R is a constant, and R is 8.31. So actually the constant here, I should have said, is N times R, not just N. So the constant here, N times R, where N is the number of moles, and R being 8.31 joules per Kelvin per mole is known as the universal gas constant. So it's true for anywhere in the universe, hence universal. And this gas constant will always be, well, constant, and you'll find this in your data sheet. Now, if I don't have the number of moles, I can do a little bit of rearranging, and I can write this equation in terms of the number of molecules. If I think back to the start of this crash course, I found I could relate the number of moles to the number of molecules. So this can also be written in another way. PV is NKT, where K here is obviously a different value. So for me to replace little n and r with big N and K, K has to be the universal gas constant R divided by Avogadro's constant Na. And it turns out that this is 1.38 times 10 to the minus 23 joules per Kelvin. And this is a special constant. It's called the Boltzmann constant. And this will also be in your formula sheet, on your data sheet rather. And so either equation is okay to use, but I guess it all depends in the problem itself on whether you're given the number of moles or number of molecules. If you remember one and not the other, it just means you may have to do an extra step, but you could still use either or for these two equations. And these are the ideal gas equations. Well, technically it's just one equation, just written in a different way, the ideal gas equation. And so we decided that if any gas obeys this equation, it is an ideal gas, which leads us on to kinetic theory. So kinetic theory is quite fascinating. So now we sort of link the macroscopic behavior of a gas, the things we can measure for a gas, to the microscopic quantities associated with molecules of that gas. You can't physically go and measure the speed of a single molecule of gas. You can try running alongside the gas and measuring it, but probably not going to work. So what we do is we use the kinetic theory of gases as a way to explain what we think is happening with the molecules of the gas, or what's happening with molecules on average, by looking at the macroscopic quantities like pressure and volume and temperature and so on. Now, for us to use the kinetic theory, we have to make some assumptions about the molecules of the gas. Okay, and some of these assumptions are as follows. The molecules of the gas must behave as hard elastic spheres. Now, you might have remembered the word elastic from AS physics, from the topic of deformation of solids and from the topic of momentum. So basically, our molecules behave as spheres, but they undergo elastic collisions, meaning that when they collide with each other, when molecules of a gas collide with each other, they conserve kinetic energy. They don't lose that energy to the surroundings. They might transmit the energy amongst themselves, but that energy is still constant before and after a collision. So all collisions between molecules are elastic. Another assumption we must make is that the volume of the molecules must be negligible compared to the volume of the containing vessel. So our gas molecules, as it should always be much smaller than the thing that is containing it. And this helps us make sure that we don't have to deal with any quantum effects, etc. So the volume of the molecules must be negligible in comparison to the volume of the containing vessel. Now, you need to know these assumptions. You also need to write them much better than I am, in full sentences. I'm just writing them in a sort of summarized form. But they could very well ask you in an exam to name a few of these assumptions. Another thing that's important is that there are no forces of attraction or repulsion between molecules. And we know this from an ideal gas as well. Ideal gases only have kinetic energy. Ideal gases do not have potential energy, meaning there are no or negligible forces of attraction or repulsion between gas molecules. So all of the energy of an ideal gas must be kinetic and not potential. And the last assumption for kinetic theory is that there are many molecules and they all move at random. So undergoing Brownian motion. We can't predict the motion of any individual particle because they are all moving randomly. They're undergoing many collisions in a short space of time. It is impossible for us to physically measure the motion of these particles one by one, since they are all moving randomly. So there is some mathematics, significant amount of mathematics here that I am going to skip. So if we do some magical mathematics, so it's mathemagic. So some mathemagic later, and I'll make another video doing this. I think you know what I'm talking about. There is a significant derivation, requires a little bit of conceptual understanding, which gives us a funny equation. PV is equal to 1/3 NMC squared, where these triangular brackets here simply mean the average of C squared. So what does this mean? What am I basically being told here? That means PV, which I was told earlier is nRT, is actually 1/3 times the number of molecules in a gas. And remember, this is only for a specific gas. So this little m here is the mass of a molecule of this gas. If it was oxygen, for example, this would be the mass of an oxygen molecule, and multiplied by the average of the speed squared. So the average of, and C here is the speed of the molecules. So I'm actually relating macroscopic quantities P and V, things I can measure on a large scale, pressure and volume I can measure, to an understanding of what's happening on the microscopic scale, the average of C squared. If I look at all of the speeds, the distribution of speeds of the molecules, and I square the speeds of the molecules and I find the average, this is what I'm finding. So if I have one molecule moving to the right, C1, the next molecule moving to the left with a speed C2, another molecule moving with a different speed to the right, C3, and so on. If I have n molecules, and what this value is, the average of C squared, we call it the mean square speed, is C1 squared plus C2 squared plus all the way, if I have n molecules, Cn squared divided by the total number of molecules I have, which I'll say is n. That's what the mean square speed is. I'll define the different terms later because I know the terminology can be a bit confusing. So later on I'll define the differences in the terminologies. But these are statistical measures: mean, mean square, root mean square, and so on. So where am I now? What I can see, and again I said I do have to make a video on the derivation of this equation because it is significant, but generally they will say show that PV is equal to 1/3 NMC squared, and they usually start you off with some of the derivation, you have to complete the rest. That could take quite a while for me to explain. So if I have that PV, or rather P, I'm going to rewrite this equation above. P is equal to 1/3, taking the V on the other side, NM over V times C squared, the average of C squared. But wait a minute. Nm is the total mass of the gas. The total mass is the number of gas molecules times the mass of each of these molecules. If I divide that by the total volume V, I get the total density of the gas. So the density of the gas, rho. Notice it looks like P, but it's not actually P. It's a slanted P, it's a rho. So this is the density of gas multiplied by the average of C squared. Not P, but rho. So always make sure your P and your rho look different. P is more upright, rho is sort of, looks like a P, but more slanted. And weirdly, it's the Greek letter for R, not P. But wait, the question that you're asking is where if PV is nkt, and at the same time PV is 1 over 3 nmc squared, well, there must be something I can do with the two right-hand sides to get some expression, and you'll be correct. Let's equate the two right-hand side. The right-hand side of the second equation is a half, or rather 1/3 nm average of c squared, and this is equal to nkt. Now the n's immediately disappear, but I'm left with the mc squared. And that reminds me of something that I've learned a long time ago called kinetic energy. But kinetic energy was a half mc squared, not mc squared. And c here is the speed. Remember, these are the speed of the molecules, not the speed of light, not the speed of an electromagnetic wave. We're just using c as it's a common convention, right, rather than v. So what I'm going to do is I'm going to write this as 2/3, and remember the n's disappear now, into a half mc squared. 2/3 times a half is a 1/3, so I return the same fraction as I do above, and this is equal to k times t. But if I look at this, if I look at the bracket specifically, a half m times the average value of the square speed is actually going to give me the average kinetic energy of the molecules. Each molecule has the same mass m, and so the average of the kinetic energy is a half m times the average of the speed squared. And so 2/3 ek is equal to k times t, which means that ek, the kinetic energy on average of the molecules of the gas, is 3 over 2 k times t. And so this is where, for your entire high school career, you've been learning that temperature is a measure of the average kinetic energy of molecules. Now you know that it's actually true. Temperature is indeed a measure of the kinetic energy of the molecules when they are moving at random. And so if I have temperature, I can immediately tell what the average kinetic energy of the gas molecules are. The higher the temperature, the higher the kinetic energy. Kind of makes sense. We have a higher temperature, the molecules move around more, and so they have a higher kinetic energy. So that's where the explanation and the equation comes from. Now we're not totally done there, because I can also go back to the equation for c squared. I can go back to the beginning, and I can say, well, from somewhere there, I can say c squared, the mean square speed, is 3kt over m. Okay, and why is this relevant? Because if I take the square root of this, so just bear with me for now, I get what we know as the RMS speed. And the RMS speed means I just need to square root the right-hand side of this equation, which is the square root of 3kt over m. And this is called the root mean square speed of molecules. Why do we use the root mean square? Why can't I simply just use the average speed of molecules? That's because for particles moving at random, I have speed c1 and speed c2 and speed c3. If I were to consider the velocities, the average velocity of these molecules, let's use c since we stuck with the convention c, the average velocity, if I consider the vector quantity, would be 0. And so when working with velocities, when working with the vector quantities, the average would be 0, because on average there'd be as many particles moving in one direction as they were in the other, as many to the right as they were to the left, as many up as they were down, and the speeds, the magnitude of the velocities, would also be the same. So on average, the gas wouldn't have a speed. There wouldn't be an average speed for the molecules, because they would all be canceling each other out, or rather there wouldn't be an average velocity. But the RMS is simply a measure we use when average doesn't work as well. So a little note on the different quantities. If you do math and statistics, you know that if I were to calculate the average of something, I can also call it the mean. And so this quantity, the average of c, means all the values of the speed added together divided by the total number of molecules we have, total number of speeds that I'm measuring, that we call the mean speed. If I take this value, whatever this average value is, and I square it, then this is called the mean speed squared. Just like if I take the number 2 and I square it, that's 2 squared. So this is the mean speed, whatever the average speed of the molecules are, and then we square that number. Like I showed you before, if the c squared is inside the triangular brackets, this is actually named differently. This is not the mean speed squared, but rather the mean square speed. And so this is the average of the square of the speeds of each of the molecules, like I showed you earlier. So that's mean square speed, not mean speed squared. It's important to recognize that these terminologies differ. And if I take the square root of that value, as you can imagine, I'm taking the square root of the mean square speed, so I add the word root in front of it, and that becomes root mean square speed. And so these are just a little note on the different terminologies. And so we've went through this like relatively quickly, relatively fast, but again you require the time to look at the derivations, to look at the definitions of ideal gases, the important concepts like the fact that ideal gases have no potential energy, only kinetic energy, and then come to these equations that we work through. So in the next video, I'll probably do a crash course on the topic of thermodynamics. Until next time, I'm Mr. K. Join us again on Everything is Relative.